And now in this lecture we'll answer two questions. In the first question, we'll find out the size of this angle APC is equals to x. So we have to find out the value of this angle x. And in the second question, we'll find out the length of this line segment CD is equals to x. So we have to find out the value of line segment x. We'll start with the first question. In the drawing, we have triangle ABC. Know that BP equals to PC. So if you define the length of BP as A, then the length of PC must also equal to A because they are equal to each other. In addition, we know that this is angle ACP equals to 30 degrees in size. This is angle ABC equals to 15 degrees in size. Again, our test is to find out the size of the value of this angle APC is equals to x. So we have to find out the value of angle x. So first of all, we will extend side AC on this triangle ABC by straight line. In the next step, we reconstruct angle of 15 degrees at point B in such a way that one leg of the angle will be side BA and the other leg will be a leg that creates 90 degrees with the leg BA. So this angle equals to 15 degrees inside according to our construction. In the next step, we'll extend this leg by a straight line until it touches the extended side CA. And we define the touching point between the extended side CA and the extended leg. This point is point M. By doing this construction, we granted the associated triangle BMC. Triangle BMC is an associated triangle because of the fact that those two angles are equal to each other and their sizes. Each of them is equal to 30 degrees in size. So here we can implement rule 20 in this associated triangle BMC. So please click on rule 20. According to rule 20, the perpendicular to the base of an associated triangle bisects the base. In the drawing, we have the associated triangle ABC. Triangle ABC is an associated triangle because AB equals to AC. BC is the base of this associated triangle ABC. According to this rule 20, the perpendicular AD to the base BC bisects the base BC. This is to say, it divides the base BC into two halves. The first half is BD, and it of course equals to the second half DC. Each half equals to BC over 2 because BC is minimum bisected. So BD equals to BC over 2. So we can actually implement rule 20 in this associated triangle BMC. BC is the base of this associated triangle BMC. So the perpendicular from point M to the base BC bisect the base BC according to rule 20. But well, the perpendicular from point M will touch the base BC. Actually, the perpendicular from point M must touch the base BC at point P and not in any other point, because of the fact that at point P is the midpoint of BC. And we know that the perpendicular bisects the base. Therefore, the perpendicular from point M must touch the base BC at point P, because BC is bisected into two halves. The first half is BP, that is equals to A, and the second half is BC, that is also equals to A. So actually, this angle equals to 90 degrees inside, and this angle also equals to 90 degrees inside, according to our construction. Because MP is the perpendicular to the base BC. In the next step, we focus on this right triangle BMP. And the right triangle BMP, sine of 30 degrees equals to MP over MB. So that is known. The right triangle BMP sine of 30 degrees equals to MP over MB. And again, in the right triangle BMP, sine of 30 degrees equals to MP over MB. We define the length of this hypotenuse MB as 2B. MP equals to 2B units according to our definition. So sine of 30 degrees equals to MP over MB. MB is 2B. So in total we should find out that sine of 30 degrees equals to MP over 2B. Sine of 30 degrees is 1/2, so we substitute sine of 30 degrees by 1/2. So 1/2 equals to MP over 2B. Here we multiply this equation by 2B, and we get that 2B over 2 equals to MP. We have 2 in the denominator, 2 in the denominator, therefore 2 will get cancelled. And finally, we found out that MP equals to B units in its length. That is to say that the MP to the base BC equals to B units in its length. So actually we found out that if A and B is 2B, then MP must be equal to B. So MP is twice as long as MP. The next step, we will focus on the big associated triangle MBC. The big associated triangle MBC. This is angle bisector AB. angle bisector AB divides angle MBC into two halves. Each half equals to 15 degrees in size. And therefore, because of the fact that AB is the angle bisector, it divides the sides of triangle MBC proportionally, according to Rule 19. So, on page 3 on Rule 19, there is also defined as angle bisector theorem. According to Rule 19, if AD is angle bisector of this triangle ABC, that is to say, AD bisects angle BAC into two halves, each half equals to theta, then angle bisector AD divides the sides of this triangle ABC proportionally. That is to say, BD over DC equals to AB over AC. So we can implement angle bisector theorem in our drawing. Well, because in our drawing, as I already mentioned before, AB is angle bisector of triangle MBC of this angle MBC in triangle MBC. Therefore, according to Rule 19, angle bisector AB divides the sides of this triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. Repeat again. Because of the fact that AB is angle bisector of this big triangle MBC, angle bisector AB divides the sides of this big triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. MB over BC equals to MA over AC. According to angle bisector theorem, that also defined as Rule 19. According to our definition, MB equals to 2B written in itself, so we substitute MB by 2B over BC. BC in total equals to A plus A, that is 2A. And it is equals to MA over MC. So in total, if we found out that according to angle bisector theorem, (2A over 2B equals to MA over MC. We have 2 in the numerator, 2 in the denominator, so 2 get cancelled. So in this side of the equation, we have to live with B over A. B over A equals to MA over MC. B over A equals to MA over AC. So in the next step, we'll focus on this triangle MPC. The triangle MPC this is line segment AP, line segment AP divides the size of this triangle MPC proportionally. That is to say B over A equals to MA over AC. So if you know that B over A equals to MA over MC. So line segment AP divides the sides of the right triangle MPC proportionally. And therefore, according to Rule 21, that is the converse rule of Rule 19, line segment AP must be angle bisector of triangle MPC. And again, because of the fact that AP divides the size of this right triangle MPC proportionally, line segment AP must be the angle bisector of this triangle MPC. So, please click on Rule 21. Rule 21 is the converse rule of Rule 19. So according to Rule 21, if we know that BD over DC equals to AB over AC, that is to say we know that angle bisector that line segment AD, we don't know that AD is a line segment, but we know that line segment AD bisects the sides of this triangle ABC proportionally. That is to say BD over DC equals to AB over AC. And because of the fact that line segment AD bisects line segment AD divides the sides of this triangle ABC proportionally, line segment AD must be the angle bisector of this triangle ABC. According to this rule, Rule 21, that is the converse rule of angle bisector theorem. So, and then now, so line segment AB divides the sides of the right triangle MPC proportionally. And therefore, according to Rule 21, that is the converse rule of Rule 19, or you can say also that it is the converse rule of angle bisector theorem, according to Rule 21, line segment AP is angle bisector of the right triangle MPC. So, as I mentioned before, according to Rule 19, that is the angle bisector theorem, if you know that AD is angle bisector of triangle ABC, then angle bisector AD divides the size of this triangle ABC proportionally. That is to say, BD over DC equals to AB over AC. And the converse rule of this rule that is also defined as angle bisector theorem is Rule 21. We don't know that AD is angle bisector, but we know that line segment AD divides the size of this triangle ABC proportionally. That is to say, we know that BD over DC equals to AB over AC, and because of the fact that line segment AP bisects divides the size of this triangle ABC proportionally, line segment AD must be angle bisector of this triangle ABC. So, Rule 19, Rule 21 is the converse rule of Rule 19. Here we know that line segment AD is angle bisector, for line segment AD bisects the size of the triangle ABC proportionally. That is to say, BD over DC equals to AB over AC. Here we don't know that AD is angle bisector, So, but we know that line segment AD but divides the size of this triangle ABC proportionally. That is to say, we know that BD over DC equals to AB over AC. Therefore, because of the fact that line segment AD bisects the size of this triangle ABC proportionally, line segment AD must be the angle bisector of this triangle ABC. So, rule 21 is the converse rule of rule 19. So repeat again, according to rule 21, because of the fact that line segment AP divides the size of this triangle MPC proportionally, that is to say, we know that B over A equals to MA over AC, line segment AP must be the angle bisector of this triangle MPC. So if line segment AP is the angle bisector of this triangle MPC, it means that it bisects this angle, that is a right angle, into two halves. Each half, of course, equals to 45 degrees in its size. So the first half is angle MPA, equals to 45 degrees in its size. This is half of 90 degrees. The second half, this is the second half, that must be also equal to 45 degrees in its size. That is to say, we can find out in total that this is angle APC, that is the angle that we are looking for. This question, it is also defined as angle X. It is equal to 45 degrees in its size. And that is the answer to the question. In total, we found out that the missing angle APC that is also defined as angle X equals to 45 degrees in its size. This is the missing angle APC equals to X and equals to 45 degrees in its size. So that is the answer to the first question. In the next step, I present to you the second question and solve the second question of this lecture. In this second question, our task is to find out the length of this line segment CD that is equal to X. So we have to find out the length of line segment X. So in the drawing, we have a semicircle. Those three line segments CQ equals to PQ equals to QE. So if we define PQ as A, then CQ and QE must be also equal to A because of the fact that they are equal to each other according to what is given as a question. We also know that point O is the center of this circle, of this semicircle. This is those two angles, the above right angles. In addition, you know that this is 9708 is equals to 5 units in itself. This is 97AB is equals to 4 units in itself. And again, that our task is to find out the length of this 97CD is equals to X. So we have to find out the value of 97X. So first of all, we will join points C and P together by a straight line. By joining points C and P, we create the right triangle CPQ. We have the rule that says that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides in the right triangle CQP, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. We also know that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right triangle CPQ? Alpha plus alpha is 2 alpha plus 9 degrees, in total must be equal to 180 degrees. So 2 alpha plus 90 degrees, in total must be equal to 180 degrees according to the rule dimension that says that the sum of the angles in any triangle is equal to 180 degrees. Here we will subtract 90 degrees from this equation and we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. 2 alpha equals to 90 degrees. Here we will divide this equation by 2 and we get that alpha equals to 90 degrees over 2 is 45 degrees. Those two angles, they are both equal to alpha, and therefore each of them is equal to 45 degrees in its size. Actually, triangle PQC is the right angle because this is the right angle. But triangle PQC is an associated triangle because those two sides are equal to each other. And we have the general rule that if a triangle is simultaneously a right angle and also associated triangle, it will always get the same three angles. One angle is 90 degrees and the other angle must be equal to 45 degrees in their sizes. So it is given us the question that CE is a straight line it is given us the question that CE is a straight line. So if we focus on the upper side of the straight line CE at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line CE at point Q? We have this angle that is right angle plus this missing angle, and total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in size. According to rule 3, of course. In the next step, we'll join points P and E together by straight line. By joining points P and E, we get the right triangle PQE. We have the rule that says that actually we don't need the rule because we have here those two sides are equal to each other and therefore triangle PQE is an associated triangle. But it is also a right angle because this is a right angle. So triangle PQE is simultaneously a right triangle and associated triangle, and therefore those two angles must be equal to 40 degrees. They inserted each of them. In the next step, we will do a construction. That is to say, we will complete this semicircle to a circle. Okay, again, we complete this semicircle to a circle. So we completed the semicircle to a circle, and then we'll extend side CE by a straight line until it touches the circle. And we define the touching point of the extended side CE with this circle. This point is point M. Likewise, we will extend side PE by a straight line until it touches the circle. And we will define the touching point of the extended side PE with this circle. This point is point N. In the next step, we will join point C and N together by straight line, those 2 points. And we'll join points M and N together by straight line. This is triangle CPN. Triangle CPN equals to 45 degrees plus 45 degrees, that is 90 degrees. Triangle CPN subset on chord CN. Again, triangle CPN, that is the right angle, subset on chord CN. So here we can implement rule 5. This triangle, so let's click on rule 5. According to rule 5, any peripheral angle that equals to 90 degrees in its size must subtend on the diameter of the circle. So in the drawing we have a circle. This is peripheral angle MAN. Know that peripheral angle MAN equals to 90 degrees in size. Therefore, according to this, all 5 peripheral angle MAN must subtend on the diameter of the circle. And indeed, peripheral angle MAN subtend on towards the element, that is the diameter of the circle. So according to this rule, all 5 any peripheral angle equals to 90 degrees in size must subtend on the diameter of the circle. So can you implement all 5? Now we're drawing. This is peripheral angle CPM that is equal to 90 degrees in size and therefore must subtend on the diameter of the circle. Peripheral angle CPM subtend on chord CN, therefore according to rule 5, chord CN must be the diameter of the circle. So and now if you found out that chord CN is the diameter of the circle, and this you say that it passes for point O, that is the center of the circle. You know that any diameter of any circle must pass for the center of the circle. So chord CN is the diameter of the circle according to rule 5. In the next step, we'll focus on this peripheral angle CMN. Peripheral angle CMN subtend on the diameter of the circle. Again, peripheral angle CMN subtend on chord CN, that is the diameter of the circle, and therefore according to rule 7, that is the converse to rule 5, peripheral angle CMN must be equal to 90 degrees in size. So please click on rule 7. According to rule 7, if a peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees in size. In the drawing, we have a circle. This is peripheral angle ACB that subtend on the diameter of the circle. AB is the diameter of the circle. Therefore, according to this rule 7, peripheral angle ACB must be equal to 90 degrees in its size. So can you implement rule 7 in our drawing? Because in our drawing, we have peripheral angle CMN that subtend on chord CN, that is the diameter of the circle. Therefore, according to rule 7, peripheral angle CMN must be equal to 90 degrees in size. So, what you mentioned before, rule 7 is the converse rule of rule 5. According to rule 5, if we know that peripheral angle equals to 90 degrees in size, then it must subtend on the diameter of the circle. The converse rule of rule 5 is rule 7. Rule 7, we know that peripheral angle subtend on the diameter of the circle, and therefore it must be equal to 90 degrees in size. Okay. So peripheral angle CMN subtend on the diameter of the circle, and therefore it must be equal to 90 degrees in size according to rule 7. Those angles are defined as vertex angles. We know that vertex angles are equal to each other. But this angle equals to 45 degrees, therefore this missing angle must be also equal to 45 degrees in size according to the rule that I mentioned. Vertex angles are equal to each other. This is the small right triangle EMN. In the small right triangle EMN, 45 degrees plus 9 degrees plus this third angle, total must be equal to 180 degrees according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Therefore, this third angle must be equal to 45 degrees in size. What is the radius of this circle? The radius of any circle starts from the center of the circle and ends on the point of the circle itself. Point O is the center of the circle. Point B is the point of the circle itself. Therefore, OB is the radius of the circle. The length of OB is OE plus EB. OE is 5, EB is 4, so in total, the radius OB equals to 5 plus 4, that is 9. So write it down, the radius of this circle equals to 9 units in its length. OA is also the radius of the circle, therefore it is equal to 9 units in its length. Likewise, OC is also the radius of the circle, therefore it is equal to 9 units in its length. And finally, ON is also the radius of the circle, therefore it is equal to 9 units in its length. In the next step, we calculate the area of this green triangle, triangle COE. What is the area of the green triangle, triangle COE? We know that the area of any triangle equals to the base of the triangle times the height over 2. Therefore, the area of the green triangle COE equals to the base of the triangle times the height over 2. The height must create 90 degrees with the base. So the area of the green triangle COE was to the base. We choose the base as CO. Times the height. But again, that the height must create 90 degrees with the base. You can say also that the height must create 90 degrees with the extended base. The extended base CO is Cn. So the height must create 90 degrees with Cn. So from point D, we go perpendicular on the base Cn, and therefore it is the height. Because it is perpendicular to the base, the extended base Cn. Again, repeat again, from point D, we go perpendicular on Cn. Will be the height to the base of this grand triangle COE. This angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point T and Cn. This point is point G. Again, EG is the height to the base, Cn. Therefore, we define EG as h, abbreviation for height. So in total, we found out that the height to the base of the green triangle COE equals to h. So the height of the green triangle COE is h over 2. So in total, we found out that the area of this green triangle COE equals to CO times h over 2. CO is the radius of this circle, therefore it is equal to 9. So substitute CO by 9, h over 2. So in total, we actually found out that the area of the green triangle COE equals to 9h over 2 square units in size. Likewise, we calculate the area of this lower triangle, triangle OEN. What is the area of the lower triangle OEN? The area of any triangle equals to the base of the triangle times the height over 2. We choose the base of this lower triangle OEN SON. The height to the base must get 90 degrees with the base. EG is equal to H gets 90 degrees with the base ON. So H is the height to the base ON of this lower triangle ON. So H is the height over 2. So we found out that the area of the lower triangle ON equals to ON times H over 2. ON is the radius of this circle, is equal to 9 times H over 2. So in total we found out that the area of the lower triangle ON equals to 9H over 2 square root in its size. But the area of the green triangle COE also equals to 9H over 2. Therefore, the area of those two triangles are equal to each other. That is to say, the area of the green triangle COE is equal to the area of the lower triangle OEN. In the next step, we calculate the area of this big triangle CEN. What is the area of the big triangle CEN? The area of triangle CEN equals to the sum of the areas of the two components that it consists of. The big triangle CN consists of those two components, that is to say it is the green triangle COE plus the lower triangle COEN. Therefore, the area of the green triangle CN must be equal to the sum of the areas of those two components that it consists of. So, the first component is this green triangle COE, so it is the area of the green triangle COE plus the area of the second component, that is triangle OEN. So in conclusion, we found out that the area of the big triangle CN equals to the area of the green triangle COE plus the area of the lower triangle OEN. But we already found out that the area of triangle OEN equals to the area of triangle COE. So in this equation, we can substitute the area of triangle OEN by the area of triangle COE because they are equal to each other. And get that the area of the green triangle CEN, the area of the big triangle CN, the area of this big triangle CEN equals to the area of the green triangle COE, and we substitute the area of the triangle OEN by the area of the green triangle COE because they are equal to each other. So it is plus the area of the green triangle COE. Because I know that the area of the big triangle CN equals to 2 times the area of the green triangle COE. So here we divide this equation by 2 and finally get that the area of the green triangle COE equals to the half of the area of the big triangle CN. This is the area of the big triangle CN over 2. We say also that the area of the big triangle CN is twice as large as the area of the green triangle COE. Okay, so the area of this big triangle CN is twice as large as the area of this green triangle COE. In the next step, we will implement rule 65 in our drawing. So I click on rule 65. Rule 65 is true in any circle, so this circle could be any circle. In any circle, if chord AB intersects with chord CD at point O, then the following equation is true. AO times OB equals to CO times OD. So, in the moment we have a circle, this is called AB, it intersects with chord CD at point O. In this moment, the following equation is true. So if two chords are intersect with each other in a circle, then the following equation is true. AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement rule 65 in our drawing. So in our drawing, chord AB intersects with chord CM at point E. Again, chord AB intersects with chord CM at point E. Point E is the intersection point of chord AB with chord CE. Again, chord AB intersects with chord CM at point E. So actually all the requirements of rule 65 are satisfied, and therefore we can implement in our drawing rule 65. So write it down. But we found out that our drawing chord AB intersects with chord CM, chord CM at point E. And therefore, according to rule 65, the following equation is true. AE times EB equals to CE times EM. And again, according to rule 65, so the following equation is true. AE times EB equals to CE times EM. AE times AB equals to CE times EM. AE equals to AO plus OE. That is to say, AE equals to 9 plus 5, that is 14. Times EB. EB equals to 4 in this according to what is given in the question. So in total, this side of the equation we have 14 times 4 equals to CE times EM. CE equals to A plus A, that is 2A. A plus A, that is 2A. Times EM. What is the value of EM? So here we have the word that says that in front of equal angles in the triangle are equal sides. So in front of, in this triangle, right triangle EMN, in front of those two equal angles, you have those two sides that must also equal to each other and their lengths. So if you define the length of EM as B, then the length of side MN must also equal to B, according to the rule that I mentioned. In front of equal angles in the triangle, there are equal sides. So EM equals to B, according to our definition. So in total, according to Rule 65, we found out that 14 times 4 equals to 2AB. 14 times 4 is 56, equals to 2AB. Here we divide this equation by 2, and finally get that AB equals to 56 over 2 is 28. So AB equals to 28. So in the next step, we calculate the area of this big triangle CN according to the rule that said that the area of any triangle equals to the base of the triangle times the height over 2. So what is the area of this big triangle CN? And again, the area of triangle CN equals to the base of the triangle times the height over 2. We choose the base of this big triangle CN as CE. Times the height. The height must rate 90 degrees with the base. We can also say that the height must rate 90 degrees with the extended base CE. The extended base CE is CM. Again, the extended base CE, the extended base CE is CM. So the height must rate 90 degrees with the extended base. The extended base is CM, so we say that MN gets 90 degrees with this extended base CM. Therefore, MN is the height to the base. Gets 90 degrees with the extended base CM. So MN is the extended base, but it is the height to the extended base over 2. CE equals to CQ, that is A, plus QE, that is also A. So CE in total equals to A plus 8, that is 2A. Times MN. MN equals to B, according to our definition, over 2. So in total we found out that the area of the big triangle CN equals to 2AB over 2. Here we have 2 in the numerator, 2 in the denominator, so 2 gets cancelled, and we left only with AB. In total we found out that the area of the big triangle CN equals to A times B squared in size. And again, the area of this big triangle CEN equals to A times B squared in size. But according to Rule 65, A times B equals to 28. So we can write it that A times B equals to 28. And from this equation, we will derive that the area of the big triangle CN equals to 28. Those two sides are equal to each other. .28 squared in size. We already found out that the area of the green triangle COE equals to the area of the big triangle CN over 2. So the area of the big triangle, the green triangle COE equals to the area of the big triangle CN over 2. Just right now found out that the area of the big triangle CN is 28, so over 2. 28 over 2 is 14. On this equation, we derive that the area of the great triangle COE equals to 14 square units in size. Those two sides of the equation are equal to each other. So if we found out that the area of the great triangle COE is equal to 14 square units in its size. In the next step, we calculate the area of this great triangle COE according to the rules that says that the area of any triangle equals to the base of the triangle times the height over 2. The area of the great triangle COE equals to the base of the triangle times the height over 2. We choose the base of this great triangle COE as OE. And the height to the base OE must rest 90 degrees with the extended OE is the base, choose OE is the base of this great triangle OEC, and the height to the base must rest 90 degrees with the extended base. OE is the base, the extended base OE is EA. Again, the extended base of EO is EA. So the height to the extended base must rest 90 degrees with the extended base EA. CD creates 90 degrees with the extended base EA. This is right angle. Therefore CD is the height to the extended base EA. EA of this great triangle COE. So the height is CD over 2. So in total, the area of the great triangle CO equals to the base OE times the height CD over 2. OE is 5 according to what is given as the question. Times CD. CD equals to X. That is the line segment that we are looking for in this question. So it is 5x over 2. So in total, if you found out those two sides of the equation are equal to each other. The area of the great triangle COE equals to 5x over 2 square units in size. But we already found out that the area of the great triangle COE equals to 14 square units in size. So we can write that the area of the great triangle COE equals to 14 square units in size. So for this equation, 14 equals to the area of the great triangle COE equals to 5x over 2. We know that those two sides of the equation are equal to each other. That is to say, 14 equals to 5x over 2. Here we multiply this equation by 2, and finally get 14 equals to 5x over 2. Here we multiply this equation by 2, and finally get that 14 times 2 is 28 equals to 5x. Here we divide this equation by 5, and finally get that x equals to 28 over 5. 28 over 5 is 5.6. So if you found out that CD equals to x, line 7 CD is equals to line 7x equals to either 28 over 5 units in this term from terms of numbers. The value of rise CD is equal to x is equal to 5.6 units in this term. And that is the answer to the second question. So in the next step, I summarize the lecture. We'll start with the repetition of the solution of the first question, and then we repeat on the solution of this second question. Our task in the first question was to find out the size of this angle APC equals to x. We had to find out the value of this angle, angle x. So in the following, we have triangle ABC. This is angle ABC. This equals to 15 degrees in size. This is angle ACB. This equals to 40 degrees in size. We know that BP equals to PC. Again, our task was to find out the graph of this, the size of this angle APC. This is equals to x. So we have to find out the value of angle x. Because of the fact that BP equals to PC, if we define BP, so then PC must also equal to A. In the next step, we did a construction. That is to say, we extended side CA by side line, and then we created angle of 15 degrees at point P in such a way that BA will be one leg of the angle, and the other leg rests 90 degrees with the angle BA, with side BA. Again, we built angle of 15 degrees at point B in such a way that one leg of the angle will be BA and the other leg will be created in such a way that it creates 90 degrees with the leg BA. So this angle equals to 15 degrees according to our construction. The next step, we extended this leg by side line until it touches the extended side CA. And we find the touching point of the extended side CA with this extended leg. This point is point M. When doing this construction, we can deduce the associated triangle, triangle BMC. Why triangle BMC is the associated triangle? Because of the fact that those triangles are equal to each other in their sizes. Each angle equals to 30 degrees. So here we have the associated triangle, triangle BMC. Therefore, we can implement rule 20 on this associated triangle, triangle BMC. So please click here on rule 20. According to rule 20, the perpendicular to the base of an associated triangle, bisect the base. Again, the perpendicular to the base of an associated triangle, bisect the base. In the following, we have the associated triangle, triangle ABC. Triangle ABC is an associated triangle because AB equals to AC. BC is the base of this associated triangle, triangle ABC. Only to this rule 20, the perpendicular AD to the base BC bisect the base BC. This is to say, divides the base BC into two halves. The first half is BD. It is of course equals to the second half, that is DC. Each half equals to BC over 2 because of the fact that BC is being bisected by the perpendicular AD. So BD equals to DC equals to BC over 2. So we can implement all 20 in our drawing. In our drawing, we have from point M, if we draw perpendicular to the base BC of this associated triangle in MBC, if we touch the base BC at point P. Why? Because at point P, the base BC has been bisected into two halves. The first half is BP, that is equals to A. The second half is PC, that is also equals to A. So the perpendicular from point M to the base BC must touch the base BC at point P, not at any other point. MP is a perpendicular, therefore this is a right angle, this is also a right angle according to our construction. In the next step, I should focus on this right triangle BMP. In the right triangle BMP, sin 40 degrees equals to MP over MB. And again, in the right triangle BMP, sin 40 degrees equals to MP over MB. To define the hypotenuse MB as 2B, and therefore sin 40 degrees equals to MP over MB is 2B. So sin 40 degrees equals to MP over 2B. Sin 40 degrees equals to MP over 2B. So sin 40 degrees is 1 half. So 1 half equals to MP over 2B. If you multiply this equation by 2, you find out that 2B over 2 equals to MP. We have 2 in the denominator, so 2 gets cancelled. But we found out that MP equals to B. MP equals to B. So we can say that if MB equals to 2B, then MP must be equal to B. The next step, we focus on the big associated triangle, triangle BMC. This is the angle bisector AB. Why AB is the angle bisector of the big associated triangle, triangle MBC? Because of the fact that the angle bisector AB bisects this angle MBC. Divides angle MBC into two halves. The first half is 40 degrees. The second half is also 15 degrees. The first half is 15 degrees and the second half is also 15 degrees. So AB is the angle bisector of the big associated triangle, triangle MBC. Therefore, we can implement here angle bisector theorem that is also defined as Rule 19. According to angle bisector theorem, if we know that AD is the angle bisector of this triangle ABC, that could be any triangle. If AD is the angle bisector, it means that it bisects angle BAC into two halves, each half equals to theta. So if we know that AD is the angle bisector, then angle bisector AD divides the sides of this triangle ABC proportionally. That is to say, BD over DC equals to AB over AC. So we can implement Rule 19 in our drawing, because in our drawing, if we relate to the big associated triangle, triangle MBC, we know that AB is the angle bisector of angle MBC in the big associated triangle, triangle MBC. And therefore, according to Rule 19, it is also defined as angle bisector theorem. Angle bisector AB divides the sides of this big associated triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. So according to Rule 19, that is also defined as angle Bassotto theorem, because of the fact that AB is angle Bassotto of this big associated triangle MBC. Angle Bassotto AB divides the size of this big associated triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. MB over BC equals to MA over AC. MB is 2B over AC. AC is 2A. Again, MB is 2B, BC is 2A, and it's equals to MA over MC. We have two denominators to get cancelled, so in this side of the equation, we have to leave B over A equals to MA over MC. We found out that B over A equals to MA over AC. So in the next step, we focus on this right triangle MPC. In this right triangle MPC, line segment AP divides the size of this triangle MPC proportionally. That is to say, B over A equals to MA over AC. And because of the fact that line segment AP divides the size of this triangle MPC proportionally, line segment AP must be the angle Bassotto of this triangle MPC according to Rule 21, that is the converse rule of Rule 19. So please click on Rule 21. According to Rule 21, if we know that line segment AD divides the size of this triangle ABC proportionally, that is to say, we know that BD over DC equals to AB over AC, then line segment AD must be the angle Bassotto of this triangle ABC. So we can implement Rule 21 in our drawing. One put in our drawing. If we focus on the line triangle MPC, line segment AP divides the size of this triangle MPC proportionally. That is to say, B over A equals to MA over AC. And therefore, according to Rule 21, line segment AP must be the angle Bassotto of this triangle MPC. And again, in the right triangle MPC, we know that line segment AP divides the size of this the right triangle MPC proportionally. That is to say, we know that B over A equals to MA over AC. Therefore, according to Rule 21, line segment AC must be the angle Bassotto of triangle MPC. Line segment AP is the angle Bassotto of triangle MPC. That is to say, angle Bassotto AP divides angle MPC into two halves. Angle MPC, the big angle MPC is right angle, so each half must be equal to 45 degrees in size. This is the first half, is equal to 45 degrees in size, and this is the second half, it must be also equal to 45 degrees in size. But it means that angle APC is equal to X equals to 45 degrees in size. So in total, we found out that the angle that we are looking for this question, that is angle APC is equal to X, is equal to 45 degrees in size. So we finish to repeat on the first solution of the first question. The next step, repeat on the solution of the second question. In the second question, our task is to find out the length of line segment CD is equal to X. We have to find out the value of line segment X. So in the drawing, we have a semicircle. Point O is the center of the semicircle. Line segment O equals to 5 units in length. Line segment AB, this is point B. This is letter B. Line segment EB equals to 4 units in length. In addition, we know that those two angles are both right angles. We also know that CQ equals to PQ equals to QE. Again, our test was to find out the left of line segment CD, this is equal to X, so we have to find out the value of line segment X. So first of all, because of the fact that CQ equals to PQ equals to QE, if we define the length of PQ as A, then the length of CQ and QE must be equal to A because they are equal to each other. But again, according to our definition, PQ equals to A, CQ also equals to A, and QE also equals to A because they are equal to each other. In the next step, we join points C and P together by third line. Repeat again, we join points P and C together by third line. By joining points C and P, we get the right triangle CQP. We have the rule that says that in front of equal sides in the triangle, there are equal angles. So the right triangle CQP in front of those two equal sides, those two sides are equal to each other, each of them is equal to A. So in front of those two equal sides, we have those two angles that must be equal to each other according to the rule that I mentioned. So if you define the size of this angle as alpha, then the size of this angle must be equal to alpha because they are equal to each other according to the rule that I mentioned. We also know that the sum of the angles in a triangle is equal to 180 degrees. So in the triangle CPQ, the sum of the angles must be equal to 180 degrees. Alpha plus alpha is 2 alpha plus 9 degrees, and total must be equal to 180 degrees. The right triangle CPQ, 2 alpha plus 9 degrees equals to 180 degrees. Here we subtracted 90 degrees from the equation, and find out that 2 alpha equals to 180 degrees minus 20 degrees is 90 degrees. Here we divide this equation by 2, and find out that angle alpha, the missing angle, equals to 90 degrees over 2, that is 45 degrees. Those two angles are both equal to alpha, and therefore each of them is equal to 45 degrees in its size. It is given as a equation that CE is a third line. So if you focus on the upper side of the third line CE at point Q, if the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles from one side of the third line is equal to 180 degrees. So which angles we have at the upper side of the third line CE at point Q, we have this angle, the right angle, plus this missing angle, total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points P and E together by third line. By joining points P and E, we get the right triangle PQE. The right triangle PQE is also an associated triangle because of the fact that those two sides are equal to each other. And we know that any right triangle that is also an associated triangle, we have always the same three angles. One angle is the right angle, and the two angles, each of them is equal to 45 degrees. Okay, so those two angles must be equal to 45 degrees in their sizes. So in the next step, we completed this semicircle to a circle, and then we extended side PE by third line until it touches the circle. We define the touching point of the extended side PE with this circle. This point is point N. Likewise, we extended side CE by third line until it touches the circle. We define the touching point of the extended side CE with this circle. This point is point M. The next step, we join points M and N together by third line. We join points C and N together by third line. This is periangle CPN. Periangle CPN equals to 45 degrees plus 45 degrees, that is 90 degrees. So periangle CPN is the right angle, and it's subset on chord CN. Here we can implement rule 5 in our formula. Basically from rule 5. According to rule 5, any peripheral angle is equal to the angle inside must subset on the diameter of the circle. We have a circle. This is peripheral MAN. We know that peripheral MAN equals to 90 degrees in size. Therefore, according to this rule 5, peripheral MAN must subtend on the diameter of the circle. And indeed, peripheral MAN subtend on chord MN, that is the diameter of the circle. So according to this rule 5, any peripheral equals to 90 degrees in size must subtend on the diameter of the circle. So we can implement rule 5 in our drawing. Why? Because in our drawing, as I already mentioned before, this is peripheral CPN. Peripheral CPN equals to 90 degrees in size. 45 degrees plus 45 degrees is 90 degrees. Therefore, according to rule 5, peripheral CPN must subtend on the diameter of the circle. Peripheral CPN subtend on quotient, and therefore quotient must be the diameter of the circle according to rule 5. In the next step, we implemented the converse rule of rule 5 on this peripheral CMN. We know that peripheral CMN, this peripheral CMN subtend on quotient, that is the diameter of the circle, and therefore according to rule 7, peripheral CMN must be equal to 90 degrees inside. Again, rule 7 is the converse rule of rule 5. So repeat quickly rule 7. According to rule 7, if a peripheral subtend on the diameter of the circle, then it is equal to 90 degrees in size. In the drawing, we have a circle. This is peripheral ACB, and we know that peripheral ACB subtend on the diameter of the circle. That is to say, we know that AB is the diameter of the circle. Therefore, according to this rule 7, peripheral ACB that subtend on the diameter of the circle must be equal to 90 degrees in size. So we can implement rule 7 in our drawing. This is peripheral CMN that subtend on the diameter of the circle, and therefore peripheral CMN must be equal to 90 degrees in size. According to rule 7. Those two angles are defined as vertex angles. We know that vertex angles are equal to each other. This angle equals to 45 degrees inside, and therefore the other angle must be also equal to 45 degrees inside according to the rule that I mentioned. This polarized angle EMN, 45 degrees plus 9 degrees, plus this 12 degrees angle, so that must be equal to 180 degrees according to the rule that says that the sum of the angles in a triangle is equal to 180 degrees, and therefore this 12 degrees angle must be equal to 45 degrees in size. In the next step, we calculated what is the radius of this circle. The radius of any circle starts from the center of the circle and ends at any point of the circle itself. Therefore, OB is the radius of the circle. Why? Because it starts from the center O and ends at point B, that is the point of the circle itself. OB in total equals to OE plus EB. OE is 5, EB is 4, according to what is given in the question. So, in total, the radius OB equals to 5 plus 4, that is 9. The radius of the circle equals to 9 units in itself. Likewise, the radius OA equals to 9, the radius ON also equals to 9, and the radius CO also equals to 9 units in itself. In the next step, we calculated the area of this green triangle, COE. What is the area of this green triangle? COE. We know that the area of any triangle equals to the base of the triangle times the height over 2. We choose the base of this green triangle COE as CO times the height. What is the height of this green triangle COE? We know that the height must rest 90 degrees with the base, or we can say also that the height must rest 90 degrees with the extended base. The extended base CO is CN. Therefore, the height must rest 90 degrees with CN. So from point D, we go perpendicular on CN, and this will be the height. So this angle equals to 90 degrees, this also angle equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point D and CN. This point is point G. EG is the height to the base, CN, and therefore we define EG as H. So the height to the base, the extended CO is H. over 2. So in total, the area of the given triangle CO equals to the base CO times the height, that is edge over 2. CO is 9, it's the radius of the circle, times the height edge over 2. So in total, we should find out that the area of the given triangle CO equals to 9 edge over 2 square units in size. Likewise, we calculated the area of this lower triangle, triangle OEN. The area of any triangle equals to the area of the base of the triangle times the height to the base over 2. We choose the base of this triangle OEN as ON, and the height to the base must get 90 degrees with the base. Edge gets 90 degrees with the base, therefore edge is the height to the base ON of this lower triangle OEN. So today we should find out that the area of the lower triangle ON equals to the base, that is ON, times the height edge over 2. ON is the radius of this circle, that is 9. So today we should find out that the area of the lower triangle ON equals to 9 edge over 2 square units in size. But the area of the given triangle COE also equals to 9 edge over 2. Therefore, we should find out that the area of the given triangle COE equals to the area of the lower triangle OEN. In the next step, we calculated the area of this big triangle CEN. What is the area of this big triangle CEN? The big triangle CEN consists of those two components, the green triangle COE and the lower triangle OEN. Therefore, the area of the big triangle CEN must be equal to the sum of the areas of the two components that it consists of. Okay, again, the area of the big triangle CN must be equal to the sum of the areas of the two components that it consists of. The first component is the green triangle COE, therefore it is the area of the green triangle COE, plus the area of the second component, that is triangle OEN, so plus the area of the second component, that is triangle OEN, the lower triangle OEN. So in total, we should find out that the area of the big triangle CN equals to the area of the green triangle COE plus the area of the lower triangle OEN. But we already found out that the area of triangle COE equals to the area of triangle OEN. The area of triangle COE equals to the area of triangle OEN. Therefore, we can substitute the area of triangle OEN plus the area of triangle COE. We did it, we can find out that the area of the big triangle CN equals to the area of the triangle COE plus the area of the triangle COE. We substitute the area of the triangle OEN by the area of the triangle COE because they are equal to each other. So today we found out that the area of the big triangle CN equals to the area of triangle COE plus the area of the triangle COE. That is to say, the area of the big triangle CN equals to 2 times the area of the green triangle COE. Here we divided this equation by 2 and found out that the area of the green triangle COE is after the area of the big triangle CN. That is to say, it is equals to the area of the big triangle CN over 2. In the next step, we implemented rule 65 in our drawing. Repeat quickly on rule 65. First of all, rule 65, it is so in any circle. So this circle could be any circle. According to rule 65, if chord AB intersects with chord CD at point O, then the following equation is to AO times OB equals to CO times OD. So we can implement rule 65 in our drawing. Why? Because in our drawing, this is chord AB that intersects with chord CM at point E. Again, chord AB intersects with chord CM at point E. So all the requirements of rule 65 are satisfied, and therefore we can implement in our drawing rule 65. But again, if we found out that chord AB intersects with chord CM at point E, therefore according to rule 65, the following equation is to AE times EB equals to CE times EM. Again, AE times EB equals to CE times EM. According to rule 65, the following equation is to AE times EB equals to CE times EM. AE equals to AO plus OE. AO is 9, OE is 5. So in total, A equals to 9 plus 5, that is 14. A equals to 14 times EB. EB equals to 4. Then again, A equals to 14, EB equals to 4, and it equals to CE times EM. CE in total equals to CQ, that is A, plus QE, that is also A. So in total, C equals to A plus A, that is 2A, plus times EM. Actually, here we have the rule that says that in front of equal angles in the triangle, there are equal sides. So in this right triangle EMN, in front of those two equal angles, we have those two sides that must also equal to each other and the reverse. So if we define the length of this side EM is B, then side MN must also equal to B, according to the rule that I mentioned, in front of equal angles in the triangle, there are equal sides. So both those two sides are equal to B. EM equals to B, and MN also equals to B. So CE is 2A times EM is B. CE is 2A and EM is B. So we found out that 14 times 4 equals to 2AB. 14 times 4 is 56 equals to 2AB. If we divide this equation by 12, we found out that AB equals to 56 over 2 is 28. AB equals to 28. AB equals to 28. The next step, we calculated the area of this big triangle CN, according to the rule that says that the area of any triangle equals to the base of the triangle times the height over 2. So the area of the big triangle CN equals to the base of the triangle times the height over 2. We choose the base of this big triangle CN is CE, and the height to the base must rate 90 degrees with the extended base. The extended base CE is CM. If we extend CE, we get CM. So the extended base CM is CM. And MN gets 90 degrees with the extended base CM. This is right again. So the height to the base is MN. So in total we found out that the area of the big triangle CN equals to the base CE times the height MN over 2. CE equals to A plus A, that is 2A, plus EM, times EM. The height MN, times the height MN, that is B. Again, the base C equals to 2A, and the height MN equals to B over 2. So here we have 2 in the denominator, so 2 will get cancelled, and left only with AB. So in total we found out that the area of the big triangle CN equals to A times B. But according to rule 65, A times B equals to 28. So we can write here that A times B equals to 28. And from this equation, we know that the area of the big triangle CN equals to 28 square in size. Those two sides of the equation are equal to each other. But we already found out that the area of the triangle CN, the area of the big triangle, the area of the great triangle COE is of the area of the big triangle CN. Again, we found out that the area of the great triangle COE equals to the area of the big triangle CN over 2. But the area of the big triangle CN equals to 28, so we can substitute the big triangle CN by 28 over 2. 28 over 2 is 14. Those two sides of the equation are equal to each other. So in total, we found out that the area of the great triangle COE equals to 14 square in size. And again, the area of the great triangle COE equals to 14 square in size. In the next step, we calculated the area of this great triangle COE according to the rule that said that the area of any triangle equals to the base of the triangle times the height over 2. The area of the great triangle COE equals to the base of the triangle times the height over 2. We choose the base of this great triangle COE as OE. The base is OE. We choose the base of this main triangle COE, SOE, and the height to the base must get 90 degrees with the extended base. The extended base OE, if we extend the base EO, we get EA. If we extend the base EO, we get the extended base EO is EA. CD definitely gets 90 degrees with the extended base EA. Again, CD gets 90 degrees with the extended base EA. So CD is the height of the base. Okay, again, we choose the base of the rectangle COE is OE, and the height to the base is CD over 2. OE equals to 5 units in itself, according to what is given as the question, and times CD equals to X. This is the answer that we are looking for. And again, according to what is given as the question, OE equals to 5 and CD equals to X. So in total, we have 5X over 2. So in total, those two sides of the equation are equal to each other. So in total, we should find out that the area of the triangle COE equals to 5X over 2. But we already found out that the area of the triangle COE equals to 14. So we can write here that the area of the triangle COE equals to 14 squares inside. And from this equation, those two sides of the equation are equal to each other. That is to say 14 equals to 5x over 2. 14 equals to 5x over 2. If we multiply this equation by 2, we find out that 14 times 2 is 28. 28 equals to 5x. If we divide this equation by 5, and find out that x equals to 28 over 5, or 28 over 5 is 5.6. So we found out that the length of this line segment CD is equals to x, it is equal to either 28 over 5 units in itself, or in terms of numbers, CD is equal to x is equal to 5.6 units in its length. Okay, thank you very much.